What if the vast emptiness of space, the very thing that makes interstellar travel so daunting, could be conquered not by conventional means, but by the strange, almost magical principles of quantum mechanics? Humanity has always looked to the stars with a mix of awe and ambition, dreaming of one day venturing beyond our solar system. But the challenges of navigating the cosmos are immense: vast distances, unpredictable environments, and the limitations of traditional technology. Enter quantum computing, a revolutionary force that might just hold the key to unlocking the secrets of interstellar navigation. Today, we're diving into how this cutting-edge technology could transform our ability to explore the universe, from solving the complex calculations required for deep space travel to enabling real-time decision-making in the most extreme conditions. By the end of this video, you'll understand why quantum computing isn't just a tool for the future, it's a game-changer for humanity's journey to the stars. So, let's embark on this fascinating exploration together and uncover how the strange world of quantum mechanics might pave the way to the distant reaches of the cosmos. Navigating the vast expanses of space is no small feat. Imagine trying to chart a course across distances so immense that even light takes years or centuries to traverse. Traditional methods of space navigation, like radio signals and optical telescopes, have served us well within our solar system. But when it comes to interstellar travel, these tools hit their limits. Take radio signals, for example. While they've been instrumental in communication with probes like Voyager 1 and Voyager 2, they're not without flaws. Radio waves travel at the speed of light, but even at that incredible pace, sending a message to a probe billions of miles away can take hours, or even days, to reach its destination. And that's just one way. If you're waiting for a response, you're looking at double that time. This light-speed delay becomes a serious hurdle when you're trying to navigate a spacecraft in real time across interstellar distances. Then there's the issue of cosmic radiation. As spacecraft venture farther from Earth, they're bombarded by high-energy particles from deep space. These particles can interfere with onboard instruments, disrupt communication signals, and even damage the spacecraft itself. It's like trying to drive through a storm with no windshield wipers. You're essentially flying blind. And let's not forget the challenge of fixed reference points. In space, there's no GPS, no street signs, no landmarks to guide you. Stars and galaxies are constantly moving, and the vast emptiness between them offers little to orient a spacecraft. Traditional navigation relies on triangulating positions using known objects, but in deep space, those objects are often too distant or too faint to be useful. The Voyager probes are a perfect example of these challenges in action. Launched in the late 1970s, they've traveled farther than any human-made object in history. Yet, even with their groundbreaking achievements, communicating with them today is a slow, painstaking process. A single command can take over 20 hours to reach Voyager 1, and that's just within our own solar neighborhood. For interstellar missions, these delays and limitations would make real-time navigation nearly impossible. But what if there was a way to overcome these obstacles? What if we could harness the power of quantum computing to revolutionize how we navigate the stars? Quantum computing, with its ability to process vast amounts of data at unprecedented speeds, could offer solutions to these age-old problems. From calculating optimal flight paths in real time to shielding spacecraft from cosmic interference, the potential applications are as vast as space itself. And that's where our journey into the role of quantum computing in interstellar navigation truly begins. Quantum computing might sound like something straight out of science fiction, but it's a real and groundbreaking field that could revolutionize how we process information. To understand it, let's start by comparing it to classical computing, the kind that powers everything from your smartphone to the most advanced supercomputers. Classical computers use bits, which are like tiny switches that can be either on or off, represented as a 1 or a 0. These bits are the building blocks of all the data and calculations we rely on today. But quantum computing, it operates on an entirely different level. Instead of bits, quantum computers use qubits. Think of qubits as having a magical ability to be both 1 and 0 at the same time. This is called superposition, and it's like spinning a coin in the air. Until it lands, it's neither heads nor tails, but somehow both. This unique property allows quantum computers to explore countless possibilities simultaneously, giving them a massive advantage in solving complex problems. But that's not all. Quantum systems also harness something called entanglement, which Einstein famously called spooky action at a distance. When qubits become entangled, their states are linked no matter how far apart they are. Change one and the other instantly responds, as if they're communicating faster than the speed of light. This interconnectedness is what makes quantum computers so powerful, enabling them to perform calculations that would take classical computers millions of years to complete. So, what does this mean for interstellar navigation? Well, the challenges of navigating the vastness of space are enormous. From plotting the most efficient routes across light years to processing the mind-boggling amounts of data from distant stars and planets, classical computers struggle to keep up. But quantum computing could change the game. Its ability to handle multiple variables and solve complex equations in a fraction of the time makes it a perfect fit for the precision and speed required to explore the cosmos. Imagine a future where quantum-powered systems guide spacecraft through the stars, unlocking new frontiers in ways we're only beginning to dream of. When we think about space exploration, the sheer scale of data involved is staggering. From mapping distant star systems to simulating the chaotic behavior of black holes, the challenges are immense. Now, here's where the divide between classical and quantum computing becomes fascinating. Classical computers, the ones we use every day, operate on binary systems processing information in bits that are either zeros or ones. They've taken us to the moon, enabled rovers to explore Mars, and helped us peer into the depths of the cosmos. But as we set our sights on interstellar travel, their limitations start to show. That's where quantum computing steps in, offering a radical shift in how we process information. Quantum computers don't rely on bits. Instead, they use qubits, which can exist in multiple states simultaneously thanks to a phenomenon called superposition. This means they can perform complex calculations at speeds that would leave even the most advanced classical computers in the dust. Imagine trying to calculate the optimal trajectory for a spacecraft traveling to Proxima Centauri, our nearest star system. A classical computer would have to evaluate each possible route one by one, a process that could take years, but a quantum computer could explore all possible routes simultaneously, drastically reducing the time needed. This isn't just theoretical. NASA has already started experimenting with quantum algorithms for mission planning. For instance, they've used quantum computing to optimize the scheduling of satellite communications, ensuring that data is transmitted efficiently across vast distances. In the context of interstellar navigation, this capability becomes even more critical. Quantum computers could simulate the gravitational interactions between celestial bodies, predict the impact of cosmic radiation on spacecraft, and even model the behavior of dark matter, all in a fraction of the time it would take a classical system. But it's not just about speed. Quantum computing also opens up possibilities for solving problems that are practically unsolvable with classical methods. Take the challenge of simulating astrophysical phenomena like supernova or neutron star collisions. These events involve mind-bogglingly complex physics, with countless variables interacting in unpredictable ways. A quantum computer could handle these simulations with ease, providing insights that could revolutionize our understanding of the universe and, in turn, improve our ability to navigate through it. So, what does this mean for the future of interstellar travel? With quantum computing, we're not just talking about incremental improvements, we're talking about a paradigm shift. The ability to process vast amounts of data, simulate complex scenarios, and optimize trajectories with unprecedented precision could make interstellar navigation not just possible but efficient. It's a game changer, and one that could bring humanity closer to the stars than ever before. Quantum entanglement is one of the most fascinating phenomena in physics, and it could hold the key to revolutionizing interstellar communication. Imagine two particles separated by billions of miles that remain intrinsically connected. When one particle's state changes, the other instantaneously mirrors that change, no matter the distance. This eerie connection, famously called spooky action at a distance by Einstein, could allow us to send information faster than the speed of light, breaking one of the greatest barriers in space exploration. This concept ties directly into quantum teleportation, a process where the state of a particle is transferred to another particle far away without physically traveling the distance. In theory, this could enable real-time communication between Earth and interstellar probes, even if they're light years apart. Picture this: a probe exploring a distant star system sends back data through entangled particles, and scientists on Earth receive that information instantly, without the years or decades of delay we currently face with radio waves. It's a game changer for interstellar navigation, where real-time updates could mean the difference between success and catastrophe. But here's the catch: maintaining entangled states over such vast distances is incredibly challenging. Entanglement is fragile, easily disrupted by interactions with the environment or even the slightest interference. Cosmic radiation, gravitational waves, or even the tiniest particles in space could break the connection. Engineers and physicists are working tirelessly to develop ways to shield entangled particles and preserve their delicate states, but it's a monumental task. Without reliable entanglement, the dream of instantaneous communication collapses. This brings us to the heart of the matter: reliable navigation systems. If we're to rely on quantum entanglement for communication, we'll need equally advanced systems to ensure probes stay on course. After all, what good is real-time data if the probe itself is lost in the void? The interplay between quantum communication and precision navigation will be crucial, shaping the future of how we explore the stars. Now, let's take a closer look at how quantum sensors could change the game for space navigation. Imagine a spacecraft traveling through the vast emptiness of interstellar space, where traditional GPS signals simply don't exist. Without a reliable way to measure its position or velocity, the mission could quickly go off course. This is where quantum sensors come into play, offering a level of precision that's light years ahead of current technology. At the heart of this innovation are quantum atomic clocks, devices so accurate they can measure time down to the tiniest fraction of a second. Unlike conventional clocks, which rely on mechanical or electronic mechanisms, atomic clocks use the vibrations of atoms, like cesium or rubidium, to keep time. These vibrations are so consistent that even over millions of years, an atomic clock would only be off by a few seconds. For interstellar travel, this means spacecraft could calculate their position with pinpoint accuracy, even in the absence of external reference points. But it's not just about timekeeping. Quantum gyroscopes are another breakthrough, capable of detecting the slightest changes in a spacecraft's orientation. Traditional gyroscopes rely on spinning wheels or lasers, but quantum gyroscopes use the principles of superposition and entanglement to measure rotation with incredible sensitivity. This allows a spacecraft to adjust its trajectory with precision, ensuring it stays on course over vast distances. What makes these technologies truly revolutionary is their ability to operate independently. Unlike current navigation systems, which depend on signals from Earth or satellites, quantum sensors can function entirely on their own. This autonomy is critical for interstellar missions where communication delays could span years. With quantum sensors, a spacecraft could navigate the stars as confidently as a captain steering a ship through calm waters. Already, researchers are making strides in this field. For example, NASA and other space agencies are testing quantum sensors in microgravity environments, proving their potential for deep space applications. And private companies are developing compact, low-power versions that could be integrated into future spacecraft. But how might these sensors fit into the bigger picture of interstellar travel? Picture a mission to Proxima Centauri, our closest neighboring star system. A spacecraft equipped with quantum sensors could continuously monitor its position, velocity, and orientation, making real-time adjustments to its trajectory. This level of precision would be essential for avoiding cosmic hazards and ensuring the mission's success. As we push the boundaries of exploration, quantum sensors could become the unsung heroes of interstellar navigation, quietly guiding us through the cosmos with unparalleled accuracy. And while the technology is still in its early stages, the possibilities it opens up are truly out of this world. Now, let's take a step into the extraordinary. Quantum computers aren't just tools for solving equations faster. They're gateways to unlocking the deepest secrets of the cosmos. One of their most groundbreaking applications lies in their ability to simulate the fabric of space-time itself. This isn't just theoretical. It's a revolutionary way to explore phenomena like gravitational waves, black holes, and the intricate dance of celestial bodies. Imagine trying to map the ripples in a pond after a stone is dropped, but instead of water, you're dealing with the very fabric of reality. Gravitational waves, for instance, are distortions in space-time caused by massive objects like colliding black holes. Traditional computers struggle to model these events with precision because of their sheer complexity. Quantum computers, however, thrive in this arena. Their ability to process vast amounts of data simultaneously allows them to simulate these cosmic events in ways we've never seen before. But why does this matter? Well, understanding gravitational waves and black holes isn't just about satisfying curiosity, it's about navigation. In interstellar space, gravitational fields aren't uniform. They twist and warp, creating chaotic environments that could spell disaster for a spacecraft traveling at incredible speeds. By simulating these fields with quantum computers, we could predict their behavior with unprecedented accuracy, essentially creating a cosmic GPS for the stars. And that's just the beginning. These simulations could also help us better understand wormholes, those hypothetical shortcuts through space-time that could make interstellar travel a reality. While we're not there yet, quantum simulations bring us closer by allowing us to test theories and explore possibilities that were once relegated to science fiction. So, what does this mean for the future of interstellar travel? It means we're not just dreaming about crossing the galaxy, we're building the tools to make it possible. With quantum computers, we're not just observers of the universe, we're becoming its explorers. But how do we actually calculate the most efficient route for an interstellar mission? This is where quantum algorithms come into play. Unlike classical computers, which struggle with optimization problems as they grow in complexity, quantum computers can process multiple possibilities simultaneously. This allows them to tackle problems like the traveling salesman problem, a classic puzzle where the goal is to find the shortest possible route that visits a set of locations and returns to the starting point. For interstellar travel, this translates to finding the most efficient path between stars, planets, or other celestial waypoints, all while minimizing fuel consumption and travel time. Imagine the challenge of plotting a course across the galaxy. A classical computer would have to evaluate each possible route one by one, a task that could take centuries for even a modest number of destinations. A quantum computer, however, can explore all potential routes at once, thanks to the principles of superposition and entanglement. This means it can identify the optimal path in a fraction of the time, a game changer for mission planning. The benefits are enormous: less fuel needed, shorter travel times, and the ability to adapt routes in real time based on new data or unexpected obstacles in space. The implications for interstellar navigation are profound. Quantum algorithms could enable spacecraft to recalculate their trajectory on the fly, avoiding hazards like asteroid fields or gravitational anomalies. They could also help missions maximize scientific output by identifying the most resource-rich or strategically significant destinations along the way. But the real breakthrough lies in their potential to make interstellar travel not just possible but practical. By reducing the time and energy required for these journeys, quantum computing could bring us closer to exploring the farthest reaches of our galaxy and beyond. As we look ahead, the integration of quantum algorithms into mission planning could redefine how we approach space exploration. The next frontier isn't just about reaching new destinations, it's about doing so in the smartest, most efficient way possible. And quantum computing is poised to lead the way. Quantum computing holds immense promise for interstellar navigation, but there's a significant hurdle standing in its way: the harsh realities of space. Out there, cosmic radiation and extreme temperatures pose a constant threat to the delicate quantum states that power these systems. Without stable quantum coherence, the very foundation of quantum computing crumbles, making it unreliable for the precision required in navigating the vast expanse of the cosmos. So, how do we overcome this? One of the most promising solutions lies in error-correcting codes. These sophisticated algorithms act like a safety net, detecting and correcting errors that arise from environmental disturbances. Think of it as a self-healing mechanism for quantum systems. By constantly monitoring and repairing the integrity of quantum bits or qubits, these codes help maintain the stability needed for accurate calculations, even in the face of cosmic interference. But error correction alone isn't enough. Another critical piece of the puzzle is cryogenic cooling. Quantum systems operate best at temperatures close to absolute zero, where atomic movement slows to a near standstill. In space, where temperatures can swing dramatically, advanced cooling technologies are essential to shield qubits from thermal noise. Imagine a quantum computer encased in a state-of-the-art cooling apparatus, insulated against the extremes of space, ensuring its qubits remain stable and ready to perform complex interstellar calculations. Now combine these two solutions, error-correcting codes and cryogenic cooling, and you've got a quantum system robust enough to withstand the rigors of space travel. This isn't just theoretical. Researchers are already developing prototypes that integrate these technologies, bringing us closer to making quantum computing a practical tool for interstellar missions. The implications are staggering. With these advancements, quantum computers could process vast amounts of astronomical data in real time, calculate optimal flight paths through uncharted regions of space, and even simulate the behavior of distant stars and galaxies. It's a game changer for humanity's exploration of the universe, turning what once seemed like science fiction into a tangible possibility. So, while the challenges are significant, the solutions are within reach. By combining cutting-edge technology with innovative engineering, we're paving the way for quantum computing to become the backbone of interstellar navigation. And as we continue to push the boundaries of what's possible, the stars might just be closer than we think. Now, let's shift our gaze outward beyond our solar system to the countless stars and planets that dot the cosmos. One of the most pressing questions in interstellar exploration is this: are there other habitable worlds out there, and how can we find them? This is where quantum computing steps in, offering a revolutionary way to tackle the immense challenges of identifying and studying exoplanets. Current telescopes like the James Webb Space Telescope are already gathering staggering amounts of data about distant star systems. They're capturing light from planets light years away, analyzing atmospheric compositions, and even searching for signs of water or other life-sustaining elements. But here's the catch: processing this data is no small feat. Traditional computers struggle with the sheer volume and complexity of information, often taking months or even years to analyze a single planetary system. Enter quantum computing. With its ability to perform calculations at speeds that would make even the most advanced supercomputers blush, quantum systems could drastically reduce the time it takes to sift through this cosmic haystack. Imagine a quantum algorithm that can instantly identify patterns in telescope data, flagging planets with the right conditions for life. Or picture a quantum simulation that models the atmospheres of distant worlds, predicting whether they could support liquid water or stable climates. These aren't just hypothetical scenarios, they're real possibilities on the horizon. But the implications go even further. By accelerating our ability to analyze exoplanets, quantum computing could help us prioritize which ones to study in greater detail. This would be a game-changer for missions like the James Webb Space Telescope, allowing scientists to focus their efforts on the most promising candidates. And as we refine our understanding of what makes a planet habitable, we'll be one step closer to answering humanity's ultimate question: are we alone in the universe? This isn't just about finding Earth-like planets, it's about paving the way for interstellar exploration. The more we know about distant worlds, the better equipped we'll be to plan missions that could one day take us there. Quantum computing, in this context, isn't just a tool for discovery, it's a bridge to the stars. So, as we continue to push the boundaries of what's possible, quantum computing stands as a beacon of hope, a technology that could unlock the secrets of the cosmos and guide us toward our next great adventure among the stars. As we push the boundaries of space exploration with quantum-powered technology, it's crucial to pause and reflect on the ethical questions that come with such advancements. The ability to navigate the stars with unprecedented precision is undeniably exciting, but it also raises important concerns about how we, as a species, choose to wield this power. One of the most pressing ethical dilemmas is resource allocation. Quantum computing is an incredibly resource-intensive field, requiring massive amounts of energy, rare materials, and cutting-edge infrastructure. Should these resources be funneled into interstellar exploration, or could they be better spent addressing urgent challenges here on Earth like climate change or global inequality? It's a question that forces us to weigh our curiosity about the cosmos against our responsibility to the planet we call home. Another ethical gray area is the potential militarization of quantum-powered space technology. History has shown us time and again that groundbreaking innovations often find their way into military applications. Could quantum navigation systems be used to develop advanced space-based weapons or surveillance tools? And if so, what safeguards can we put in place to ensure these technologies are used for peaceful exploration rather than conflict? These aren't just hypothetical scenarios, they're decisions that will shape the future of humanity's relationship with space. Then there's the matter of extraterrestrial ecosystems. As we venture farther into the cosmos, we may encounter worlds teeming with life, even if it's in forms we don't yet understand. How do we ensure that our presence doesn't inadvertently harm these ecosystems? The idea of interstellar contamination, whether biological or technological, is a genuine concern. We have a responsibility to approach these new frontiers with humility and care, recognizing that we are visitors in a vast and interconnected universe. These ethical considerations aren't just abstract debates, they're foundational to how we move forward as a spacefaring civilization. They challenge us to think deeply about our values, our priorities, and the legacy we want to leave behind as we reach for the stars. As quantum computing continues to revolutionize interstellar navigation, it's up to us to ensure that this journey is guided not just by technological innovation, but also by a profound sense of responsibility and respect for the cosmos we are only beginning to understand. Now, let's take a leap beyond our solar system and into the vast unknown, where the search for extraterrestrial intelligence, or SETI, has captivated humanity for decades. What if quantum computing could revolutionize this quest? Imagine sifting through the endless streams of data collected by radio telescopes, searching for that one faint signal that might reveal we're not alone. Traditional computers struggle with the sheer volume and complexity of this data, but quantum computers, with their unparalleled processing power, could change the game entirely. These machines could analyze patterns in radio waves far faster than classical systems, identifying anomalies that might hint at intelligent origin. Think of it like finding a needle in a cosmic haystack, except the haystack is light years wide, and the needle might be a whisper from an alien civilization. Quantum algorithms designed to sift through noise and randomness could isolate potential signals with incredible precision, bringing us closer to answering one of humanity's oldest questions: are we alone in the universe? But what happens if we do find something? The implications are staggering. Quantum computing wouldn't just help us detect signals, it could also play a crucial role in decoding and understanding them. Imagine trying to interpret a message written in a language no human has ever encountered. Quantum systems, with their ability to process and analyze complex patterns, might help us unravel the meaning behind these interstellar communications. It's like being handed a book in an alien script. Quantum computing could be the key to translating its pages. And let's not forget the role of navigation in this grand endeavor. If we do discover intelligent life, the next step would be figuring out how to reach out or even travel to their location. Quantum computing could optimize interstellar navigation, calculating trajectories and energy requirements with unprecedented accuracy. It's not just about finding them, it's about bridging the unimaginable distances between us. This interplay between detection, communication, and navigation could redefine our place in the cosmos, opening doors to possibilities we've only dreamed of. Now let's dive into the fascinating partnership between quantum computing and artificial intelligence, a collaboration that's reshaping how we think about navigation, especially in the vastness of space. At the heart of this synergy is AI's ability to learn, adapt, and make decisions in real time, all while leveraging the immense computational power of quantum systems. Together, they form a dynamic duo capable of tackling challenges that would be impossible for classical computers alone. Imagine a scenario where a spacecraft is hurtling through deep space, navigating through uncharted regions filled with gravitational anomalies, debris, and unpredictable conditions. A quantum computer, with its ability to process vast amounts of data simultaneously, could crunch the numbers needed to plot a safe course. But here's where AI steps in. By analyzing patterns in the data, AI can refine the calculations, predict potential hazards, and even adjust the trajectory on the fly. It's like having a co-pilot that learns from every twist and turn, constantly improving its ability to guide the spacecraft through the cosmos. This isn't just theoretical. Researchers are already exploring how AI can enhance quantum navigation, For instance, scientists at institutions like NASA and the European Space Agency are developing algorithms that combine quantum computing speed with AI's adaptability. These algorithms can process complex datasets such as gravitational wave measurements or star mapping data to create highly accurate navigation models. In fact, some early experiments have shown that AI-driven quantum systems can reduce navigation errors by significant margins, making interstellar travel safer and more efficient. But the potential doesn't stop there. As quantum computers become more powerful, AI could unlock entirely new ways of navigating. Think about how self-driving cars use AI to interpret their surroundings. Now apply that same concept to a spacecraft exploring a distant galaxy. AI could analyze real-time sensor data, identify safe landing zones, or even detect signs of life on alien planets. It's a vision of the future where technology works in harmony to push the boundaries of what's possible. Looking ahead, the future of AI-driven quantum navigation is brimming with possibilities. As quantum hardware improves and AI algorithms become more sophisticated, we could see navigation systems that are not only faster and more accurate, but also capable of autonomous decision-making in the most extreme environments. From guiding probes through asteroid fields to charting courses across interstellar distances, this partnership could redefine how we explore the universe. And while we're not quite there yet, the groundwork being laid today is bringing us closer to that future, one quantum calculation and AI decision at a time. Now, let's take a step into one of the most mind-bending intersections of science and technology: quantum computing and the multiverse theory. At first glance, these two fields might seem worlds apart, one rooted in the tangible realm of advanced computation, the other in the abstract, speculative domains of theoretical physics. But when you dig deeper, you'll find they're deeply intertwined, and their connection could reshape not just how we understand reality, but how we navigate the cosmos. Quantum computing operates on principles that defy classical logic: superposition, entanglement, and the probabilistic nature of particles. These same principles are at the heart of the multiverse theory, which suggests that every possible outcome of a quantum event spawns a new, parallel universe. In other words, for every decision you make, there's a version of you in another universe who made a different choice. It's a dizzying thought, but what if quantum computers could help us explore these alternate realities? Here's where it gets fascinating. Quantum computers, with their ability to process vast numbers of possibilities simultaneously, might one day simulate these alternate universes. Imagine running a quantum simulation that maps out the branching paths of the multiverse, showing us how different choices or events could ripple across realities. This isn't just science fiction, it's a potential application of quantum computing that could deepen our understanding of the multiverse and, by extension, the nature of existence itself. But how does this tie into interstellar navigation? Well, if we can simulate alternate universes, we might also uncover insights into the fundamental laws of physics that govern them. For instance, what if certain universes have slightly different physical constants, like the speed of light or the strength of gravity? Understanding these variations could help us predict how our own universe behaves under extreme conditions like those encountered during interstellar travel. It could even lead to the discovery of new navigation strategies, leveraging quantum principles to chart safer, faster, or more efficient routes through the stars. This intersection of quantum computing and the multiverse theory isn't just about pushing the boundaries of science, it's about expanding our horizons, both literally and figuratively. By exploring these alternate realities, we might not only redefine our place in the cosmos, but also unlock tools that make the dream of interstellar travel a tangible reality. And who knows, maybe one day as we journey through the stars, we'll carry with us not just the knowledge of our universe, but the infinite possibilities of all the others. Now, let's shift our focus to how quantum computing could transform the very blueprint of spacecraft design. Imagine a world where the materials used to build interstellar vessels are not just strong or lightweight, but perfectly optimized for the extreme conditions of space. Quantum computing has the potential to make this a reality by analyzing countless combinations of materials at an atomic level, identifying the ideal properties needed for durability, heat resistance, and energy efficiency. This isn't just about making spacecraft better, it's about making them smarter, more adaptable, and capable of withstanding the rigors of deep space travel. But the impact doesn't stop at materials. Quantum computers could also revolutionize propulsion systems. Traditional methods of testing and refining propulsion technologies are time-consuming and costly, often requiring years of trial and error. With quantum computing, we could simulate these systems in a fraction of the time, exploring countless configurations and variables to find the most efficient and powerful designs. Think of it as a digital sandbox for engineers, where they can experiment with ideas that were once deemed too risky or impractical to test in the real world. This could lead to breakthroughs in propulsion, such as advanced ion drives or even entirely new concepts like warp drives, bringing us closer to the dream of faster-than-light travel. Energy efficiency is another area where quantum computing could shine. Spacecraft rely on energy sources like solar power or nuclear reactors, but optimizing their output and storage is a complex challenge. Quantum systems could model energy flow and storage with unprecedented precision, ensuring that every watt of power is used effectively. This could extend mission lifespans, reduce the need for refueling, and even enable entirely new types of missions that were previously impossible due to energy constraints. Perhaps one of the most exciting possibilities is the ability to simulate and test new technologies before they're ever built. Quantum computers could create highly accurate virtual environments where engineers can stress test designs, predict failures, and refine solutions without the need for physical prototypes. This not only speeds up the development process but also reduces costs and risks, making interstellar travel more feasible than ever before. These advancements in spacecraft design are not just theoretical, they're directly tied to the challenges of interstellar travel. The vast distances, harsh environments, and extreme speeds required to explore beyond our solar system demand a level of innovation that traditional computing simply cannot provide. Quantum computing offers a way to tackle these challenges head-on, paving the way for spacecraft that are not only capable of reaching distant stars but also surviving the journey. It's a game changer and one that could redefine our understanding of what's possible in space exploration. But what if the key to humanity's survival and expansion lies not just in reaching the stars but in thriving among them? Quantum computing could be the catalyst that transforms space colonization from a distant dream into a tangible reality. By harnessing the immense power of quantum systems, we could tackle some of the most daunting challenges of settling distant star systems problems that classical computers would struggle to solve within a human lifetime. Take resource management, for example. On a distant planet, every drop of water, every ounce of fuel, and every breath of air becomes a precious commodity. Quantum algorithms could optimize the distribution and recycling of these resources in real time, ensuring that colonies remain self-sustaining even in the harshest environments. Imagine a system that predicts supply shortages before they happen, adjusts energy consumption patterns dynamically, and even identifies new ways to extract vital materials from alien terrains. Quantum computing doesn't just solve these problems, it revolutionizes how we think about survival in space. Life support systems are another area where quantum computing could shine. Maintaining a stable environment for human life in the vacuum of space requires an intricate balance of temperature, pressure, oxygen levels, and more. A quantum-powered system could process vast amounts of environmental data simultaneously, detecting subtle changes and making split-second adjustments to keep colonists safe. It's not just about reacting to problems. It's about anticipating them, creating a living environment that feels as natural as Earth itself. And then there's terraforming, the ultimate challenge of transforming barren worlds into habitable ones. This process involves simulating and manipulating entire ecosystems on a planetary scale, a task so complex that it's nearly impossible with today's technology. Quantum computers, however, could model these ecosystems with unprecedented accuracy, testing countless variables and scenarios to find the most effective ways to introduce life to a new world. From seeding atmospheres with the right mix of gases to engineering microorganisms that thrive in alien soil, quantum computing could turn the science of terraforming into an achievable reality. The long-term implications are staggering. If humanity can harness quantum computing to overcome these challenges, we're not just talking about survival, we're talking about thriving. Colonies on distant planets could become self-sufficient hubs of innovation, culture, and exploration, ensuring that our species endures even if Earth faces catastrophe. But none of this would be possible without the ability to navigate the cosmos with precision and confidence. After all, what good is a thriving colony if we can't find our way to it? Quantum computing doesn't just help us reach the stars, it helps us chart a future among them. As we peer into the vast expanse of the universe, one of the most perplexing questions remains: what exactly are dark matter and dark energy? Together, they make up more than 95% of the cosmos, yet we've barely scratched the surface of understanding their true nature. This is where quantum computing steps in, offering a revolutionary way to tackle these cosmic mysteries. Quantum computers, with their ability to process vast amounts of data at incredible speeds, are uniquely suited to analyze the complex signals and patterns generated by particle accelerators and space telescopes. These machines don't just crunch numbers faster, they approach problems in entirely new ways. For example, when studying data from experiments like the Large Hadron Collider, quantum algorithms could identify subtle patterns that classical computers might miss, potentially revealing clues about the elusive particles that make up dark matter. Similarly, space telescopes like the James Webb or Hubble capture enormous amounts of data about the universe's expansion, which is influenced by dark energy. Quantum computing could sift through this data with unprecedented precision, helping scientists model the behavior of dark energy and understand how it drives the universe's accelerating expansion. This isn't just about solving abstract puzzles, it's about uncovering the fundamental forces that shape everything around us. But why does this matter for interstellar navigation? Imagine trying to chart a course across the galaxy without fully understanding the forces that govern space itself. Dark matter and dark energy influence the structure and motion of galaxies, meaning a deeper comprehension of these phenomena could refine our ability to predict gravitational fields, cosmic winds, and other factors critical for long-distance space travel. In essence, the more we learn about the universe's hidden building blocks, the better equipped we'll be to navigate its vast, uncharted territories. So, while quantum computing's role in decoding dark matter and dark energy might seem like pure science today, its implications stretch far beyond into the very fabric of how we explore the stars. Quantum computing might hold the key to one of science fiction's most tantalizing ideas, the discovery of wormholes. These hypothetical tunnels through space-time, often depicted as cosmic shortcuts, could potentially allow spacecraft to travel vast distances in the blink of an eye. But how do we go from theory to reality? This is where quantum computing steps in. Unlike classical computers, which struggle with the mind-bending complexity of general relativity and quantum mechanics, quantum computers thrive in this realm. Their ability to process multiple possibilities simultaneously could help us model and identify the conditions under which wormholes might exist. Imagine running simulations that test the stability of these theoretical structures or calculating the precise energy requirements to sustain them. These are problems so complex that even the most advanced supercomputers today would take centuries to solve. Quantum computing could crack them in a fraction of the time. But finding a wormhole is only the first step. Studying it presents its own set of challenges. For instance, how do we confirm its existence without physically traveling through it? Quantum sensors, powered by the same technology, could be deployed to detect the subtle gravitational signatures that a wormhole might leave behind. These sensors could measure distortions in space-time with unprecedented precision, giving us the first tangible evidence of these elusive phenomena. And if we do find one, the implications for interstellar travel are staggering. A wormhole could reduce a journey that would take thousands of years to mere moments, opening up the galaxy in ways we can barely imagine. Yet, the road to harnessing wormholes is fraught with hurdles. The energy required to stabilize and traverse one is beyond our current capabilities, and the potential risks are immense. What if a wormhole collapses mid-journey or leads to a hostile or uninhabitable region of the universe? These are questions that quantum computing could help us explore, but they also remind us of the immense responsibility that comes with such a discovery. The idea of wormholes isn't just about faster travel, it's about reshaping our understanding of the cosmos and our place within it. And as we inch closer to this possibility, quantum computing stands as a powerful tool in our quest to unlock the universe's deepest secrets. So, how exactly could quantum computing change the way we map the vast, intricate fabric of space-time? Picture this: space-time, as Einstein described it, is like a giant cosmic trampoline, warped and twisted by massive objects like stars and black holes. Navigating through this distorted landscape requires incredibly precise calculations, especially when you're dealing with regions where gravity isn't just strong, it's chaotic. This is where quantum computing steps in, offering a toolset that's exponentially more powerful than anything we've had before. Traditional computers, even the most advanced ones, struggle with the sheer complexity of space-time mapping. They rely on binary systems, ones and zeros, to process information, which works fine for many tasks but hits a wall when it comes to simulating the unpredictable behavior of gravitational fields. Quantum computers, on the other hand, operate using qubits. These qubits can exist in multiple states at once, allowing them to process a staggering number of possibilities simultaneously. Think of it like this: while a traditional computer would have to explore each path through a maze one by one, a quantum computer could explore every possible route at the same time. This capability makes quantum computing uniquely suited for creating detailed, dynamic maps of space-time. By simulating the gravitational effects of massive objects like black holes or neutron stars, a quantum computer could predict how their intense gravitational pull would warp the surrounding space. This isn't just about avoiding collisions, though that's a huge benefit. It's also about finding the most efficient routes through the cosmos, saving time, fuel, and energy for interstellar missions. Imagine a spacecraft traveling near a black hole. Without accurate space-time mapping, it could easily be pulled off course or trapped in a gravitational well. But with quantum computing, we could chart a safe path around these hazards, ensuring the mission stays on track. But the implications go even further. Detailed space-time mapping could also help us explore regions of the universe that are currently off-limits. For example, the area around a supermassive black hole is filled with extreme gravitational forces and swirling debris. Navigating through this chaos would be nearly impossible with today's technology, but quantum computing could provide the precision needed to make it feasible. This opens up entirely new possibilities for interstellar exploration, allowing us to venture into areas that were once considered too dangerous or unpredictable. And let's not forget the broader impact. If we can map space-time with this level of detail, it doesn't just benefit spacecraft, it could revolutionize our understanding of the universe itself. We could gain new insights into the nature of gravity, the behavior of black holes, and even the structure of space-time on a cosmic scale. This isn't just about avoiding obstacles, it's about unlocking the secrets of the cosmos and pushing the boundaries of what we thought was possible. So, as we look to the stars and dream of traveling among them, quantum computing might just be the key that turns those dreams into reality. As we venture deeper into the mysteries of interstellar travel, one question looms larger than any technical challenge. What happens to human consciousness during these unimaginably long journeys? Quantum computing doesn't just promise to revolutionize navigation or data processing, it might also reshape how we understand the very fabric of our minds. Theories like quantum consciousness suggest that the human brain could operate on principles not entirely unlike those of quantum systems, with superposition and entanglement playing a role in how we think, perceive, and even experience time itself. Now, imagine being on a spacecraft hurtling through the void of space for decades or even centuries. The isolation, the vast emptiness, the sheer scale of time. These factors could fundamentally alter how we experience reality. Could quantum computing, with its ability to process information in ways that defy classical logic, help us adapt to these extreme conditions? Some scientists propose that quantum-enhanced technologies might one day interface with our brains, helping us process information faster, maintain mental clarity, or even expand our perception of time. It's a mind-bending idea, quantum computers not only guiding our ships but also guiding our minds. But this isn't just about survival, it's about transformation. If quantum consciousness theories hold weight, interstellar travel could become a journey not just through space but through the very nature of what it means to be human. Could our understanding of self evolve alongside our technology? Could we develop new ways of thinking, feeling, and connecting with others across the cosmos? These questions blur the line between science and philosophy, reminding us that the greatest frontier we face might not be the stars themselves, but the uncharted territories within our own mind. And yet, even as we ponder these profound possibilities, we can't forget the human element at the heart of it all. Interstellar navigation isn't just about algorithms, coordinates, or quantum bits, it's about people. It's about the courage to explore, the curiosity to push boundaries, and the hope that no matter how far we go, we'll still carry with us the essence of what makes us human. Quantum computing may light the way, but it's our humanity that will guide us through the stars. Imagine a distant future, thousands of years from now, when humanity has spread across the stars. What if by then the stories, achievements, and knowledge of Earth are lost to time? This is where quantum computing steps in, not just as a tool for solving complex problems, but as a guardian of our legacy. One of its most profound applications could be preserving Earth's culture and knowledge for future interstellar civilizations, ensuring that even if our planet fades into history, our essence remains alive. Quantum computing offers a revolutionary way to store and encode information. Traditional data storage methods like hard drives or optical disks degrade over time and are vulnerable to environmental damage. But quantum systems could store data in quantum states, tiny, stable particles that can hold vast amounts of information. These quantum states are incredibly resilient, capable of surviving extreme conditions like cosmic radiation or the vacuum of space. This durability makes them ideal for long-term preservation, potentially lasting for millennia without degradation. Think of it like this: instead of carving words into stone, we're encoding them into the very fabric of reality. Quantum states can represent not just text or images, but entire cultural experiences, music, art, even the nuances of human emotion. By leveraging quantum entanglement, where particles remain connected across vast distances, we could create a network of quantum archives scattered across the galaxy. These archives would act as time capsules, accessible to any civilization advanced enough to decode them. But why does this matter for interstellar exploration? Preserving Earth's legacy isn't just about nostalgia. It's about creating a foundation for future civilizations to build upon. Imagine a young species on a distant planet discovering these quantum archives. They wouldn't just learn about Earth, they'd gain insights into science, philosophy, and art that could inspire their own progress. In a way, quantum computing becomes a bridge between worlds, connecting humanity's past to the future of the universe. This concept also raises fascinating questions about how we choose what to preserve. Would we focus on scientific breakthroughs, cultural milestones, or the everyday stories of ordinary people? The challenge lies in curating a legacy that reflects the full spectrum of human experience, ensuring that future civilizations see us not just as explorers, but as beings who dreamed, created, and connected. As we push the boundaries of interstellar travel, quantum computing could become an essential tool not just for navigation, but for ensuring that humanity's story endures. It's a reminder that our journey isn't just about reaching new stars, it's about carrying the light of our past into the vast unknown. And with quantum technology, that light could shine forever. But as we look toward the stars and dream of harnessing quantum computing for interstellar navigation, we're faced with a set of formidable challenges that stand between theory and reality. Scaling quantum computing for the harsh, unpredictable environment of space isn't just about making calculations faster. It's about reimagining how these systems can survive and thrive where no human can intervene. First, there's the issue of power. Quantum computers, as we know them today, require incredibly precise conditions to function. Many rely on supercooling systems that demand massive amounts of energy that's simply not available on a spacecraft light years away from Earth. Add to that the size constraints of interstellar probes, which need to be compact and lightweight to travel efficiently. Current quantum processors, with their bulky supporting infrastructure, are far from fitting into the sleek designs of spacecraft like Voyager or New Horizons. Then there's the question of autonomy. In deep space, communication delays mean that any system must operate independently, correcting errors and recalibrating itself without human input. Quantum computers are notoriously sensitive, prone to errors caused by even the slightest environmental disturbances. For interstellar missions, we'd need quantum systems that can not only self-correct, but also adapt to the unknown conditions of space, whether it's cosmic radiation, extreme temperatures, or the vacuum itself. So how do we bridge this gap between the lab and the cosmos? Researchers are already exploring innovative solutions. Some are working on developing quantum systems that operate at higher temperatures, reducing the need for energy-intensive cooling. Others are experimenting with miniaturized quantum processors that could fit within the tight confines of a spacecraft. And then there's the exciting field of quantum error correction, where new algorithms are being designed to make quantum systems more resilient to the chaos of space. It's a journey that's just beginning, but one that holds immense promise. From the theoretical breakthroughs of the past to the practical challenges of today, the path to interstellar quantum navigation is a testament to human ingenuity. As we continue to push the boundaries of what's possible, we're not just solving technical problems, we're paving the way for humanity to reach beyond our solar system and into the unknown. As we wrap up this journey into the role of quantum computing in interstellar navigation, it's clear that this technology represents more than just a leap forward. It's a complete reimagining of what's possible. Quantum computing has the potential to solve problems that are currently beyond our reach, from mapping the vast distances of space with unprecedented precision to enabling real-time decision-making for spacecraft traveling light years away. It's not just about faster calculations, it's about unlocking entirely new ways of understanding and navigating the cosmos. But let's not forget the bigger picture. This isn't just about technology, it's about humanity's future. The ability to explore distant star systems, uncover the secrets of the universe, and perhaps even find other forms of life hinges on our ability to push the boundaries of science and innovation. Quantum computing could be the key that opens the door to these possibilities, but it's only the beginning. There are still immense challenges ahead, from stabilizing quantum systems to integrating them into practical space missions. The journey won't be easy, but it's one worth pursuing. So, what does this mean for you? It's a reminder that the future is shaped by curiosity, creativity, and collaboration. Whether you're a scientist, a student, or simply someone fascinated by the mysteries of the universe, you have a role to play in this story. Stay curious, ask questions, and don't be afraid to dream big. After all, every great discovery starts with a single question. What will we discover when we finally harness the power of quantum computing to explore the stars? The answer is out there, waiting for us to find it.